Hello. So there are 2 hours today, one until lunch and one after lunch. And there are 2 things I would like to do. It's go over the examples I didn't start yesterday. And I would like again to go over this derivation because it's interesting to see, the one that gave me so much trouble early in the morning. Let me review briefly the story about the trade-offs of large-scale learning. And I think maybe the good slide is this. If you plot the test error versus the computing time, and you change the number of examples, you get several curves like this, and they tend to cross like that. And if you change the algorithms, change the optimizer, you get a bunch of curves. And we would like to be at the bottom of this series of curves. And the argument that the way to do it was to balance the various terms of the excess error. So there is the term that represents how much we lose because we optimize, or we search the optimum within a finite set of functions. How much we lose because we have a finite training set, and how much we lose because we don't optimize completely. And there are a bunch of results that basically are statistical in nature that show that this excess error has this kind of a form. And that tells you already that there is no point pushing the accuracy of the optimization beyond the accuracy of the estimation, because that will work that we lost, basically. The overall accuracy would be still dominated by the accuracy of the estimation. And in the end, we want to make all these things pretty much equal. And when you run an asymptotic analysis, you find out that the second order gradient descent, that is Newton, is something that would be a very good optimization algorithm. And the stochastic gradient descent is a very bad optimization algorithm because it has a rate that's in 1 over rho instead of log 1 over rho. But when you transform this in terms of the excess error on the testing set, and you do that by choosing the number of examples and choosing the accuracy in a way that balances everything, you find out that the stochastic gradient seems to be at least as fast, if not faster. And the question now is to benchmark this. So historically, in the machine learning community, stochastic gradient was associated with backpropagation in multi-layer networks. And multi-layer networks have a bad reputation of being hard to optimize. First of all, they're very hard problems. They're nonlinear, they're non-convex, and they're hard to debug, and that's probably most of the problem. I put this in red because it's going to happen to everyone. Always check the gradients. Just last week, I was looking at a piece of code that was a piece of bioinformatics, of proteomics, that has been used to find new proteins and everything. And on some data set, it didn't work. And the person was fiddling with the learning rates and everything. And that didn't change anything. And my advice was check the gradients. And no, this code has been running for 1 year, and the gradients are right, it works. No, check the gradients. Because in fact, suppose you make a mistake in, let's say, 20% of the gradients. The sign is wrong. It's still going to converge, still going to work. Sort of, OK. Once in a while, you're going to have a training set when it's not going to work. And fiddling with the learning rates is not going to change anything. So the only thing you have to do whenever there is a problem is not fiddling with the learning rates. Make it small so that you don't have any problem. Make it constant and small. And make sure that after you update the parameters, the error moves exactly by the amount you expect. If it does not, check the gradients. But anyway, you might wonder what is difficult, the stochastic gradient or the multi-layer networks. So the idea of this benchmark is to try the plain stochastic gradient on a simple learning problem. And the code can be downloaded. It's very simple, it's very short. And my first problem is a text categorization problem with SVM. And that's an interesting problem because text categorization was one of the poster child of SVM and one of the things that SVM did well. So I take the Reuters RCV1 document corpus. I take about 800,000 examples for training, 25,000 for testing because this is what was left. The dimension is about 50,000, so it's not really a small problem. It's not that large because it's very sparse. Each set of features is in fact one per word, basically. And each document has a couple thousand words at most. So it's quite sparse. So the task is to recognize document of a certain category. That's the that's the dominant category, so that is sort of balanced. And I minimize this cost function, basically. Regularization term plus the loss, and the loss, I'm going to use the hinge loss and the log loss just for comparison. And the update is the plain stochastic gradient with pretty much no tricks. We'll go into more details. So the lambda parameter 10 to the minus 4 was chosen not because it's the best one, but because it's the one that was in the literature for that problem. And if you run this with a standard SVM problem, like SVM Lite, which actually has a special mode for linear, actually not this one, sorry. It takes about 6 hours, and you get a certain text error. Thorsten Joachims has a new version of SVM that's linear, that uses a kind of cutting plane algorithms. This is quite sophisticated. It takes about 1 minute, which is a big progress. But the plain stochastic gradient takes 1.4 seconds. Yes?
And how does linear perform on this?
The liblinear, the Tron one, which was the old one, is probably in the 60 seconds as well.
Yeah, but
the new one is something different that came later. Yeah. That's also a stochastic algorithm with a different bias.
It's basically a stochastic gradient descent in the dual.
Yeah, it's a stochastic gradient descent in the dual. So I decide to, again, take some risk and make it run. So that's the thing. This time I take a better lambda because this one e minus 4 is not good enough. You want a smaller one. And the reason that in the literature you find the 10 to the minus 4 is because everything was slow, they couldn't test many of them. So they adjusted the lambda on a smaller set, and they hope that the same one is going to work on a larger set. When you have a larger set, you need to regularize less. And in this case, it's quite clear. So the first part is to load the data. It's loading. It's still loading, which is a problem, actually, because loading the data takes longer than training. Now it's training. It seems to go a bit slower because, in fact, after every go over all the examples, I start measuring a lot. I'm measuring the training error. I'm measuring the test error to have a validation. So I'm spending more time measuring than training as well. So you see, well, I'm not joking. There are about close to 1 million examples, 50,000 dimensions. And well, you see the training cost that reduces, and the testing cost as well, and the training error is just reduces as well. So that's quite fast. And we think, is it a super optimized program, something very complicated? And the answer is not. It's all here. So let me write the formula, and you'll see the. So it's W becomes. So I'm going to write it under that form, times 1 minus lambda eta t plus minus. So there is a bias term. So in the code, there is a little trick. The little trick is that we want to use sparsity. So the W vector is, in fact, represented as a scalar times a vector. So that's the training routine. These are the indices of the examples in the training set. This is XP here. Maybe I should use the pointer. Can I do that? Yes. So that's the training patterns, and the training labels, and that's just for printing. So OK, I go over all my examples in sequence because they've been shuffled already. I get my first pattern. So S vector is a class for sparse vectors. I get my label, plus or minus 1. I compute the dot product, and I multiply by this W scale because the W actually is a scale version of the parameters. So dot product of W and X times W scale. I compute the eta, which is 1 over lambda times t. And there is a trick that it doesn't start at t equals 0. It starts at t equal quite a large value to make sure that they're not too large. I compute y times wx plus bias, and I start my update. So to do this part here, multiplying by 1 minus lambda eta, I just multiply the scale. And if the scale is too small, I readjust everything. And the idea of doing this is because my gradients and my examples are very sparse. So if I wanted to scale the actual vector, I would have to go over all the parameters. That way, I just go over the scalar, and I'm done. But once in a while, I go over everything to make sure that I don't have numerical problems. Then I compute these things, eta t times the derivative of the loss. And I just add it to my weights with the proper ratio. So I have to divide by W scale because the weights are scale by scale. And I do the same thing on the bias, but with a trick that I go a little bit slower on the bias because the bias, we hit it all the time. And well, it's a form of Newton for the poor. And I go to the next iteration. This is what you saw running. So it's not a complicated algorithm at all. If you want to display the core of SVM Lite or the core of SVM Perf, it's not going to fit on one page.
Is this with the support vectors already chosen?
No.
No? Oh,
No. It's support vector, but it's linear, in fact. I'm just updating in the primal. This is working in the primal. So it's a support vector machine in the primal. It's just a linear discriminant function. It's a simple machinery. If you want to do it with support vectors, you actually can, but you have to pay a cost because you have to compute the part of the gram matrix you want actually to work on.
And you also need to project onto the constraint.
Yeah, you need to project on the constraint, and you have sparsity issues as well. Like if you work on the set of dual coordinates, one of the attractions of support vector machines is that they're quite sparse, but if you have a very noisy process, they're not going to be sparse in the transient. So you're going to pay a little bit for that. But see, there is nothing nasty here. It's technology from the 50s, Robinson Monroe. Now, of course, I find sometimes embarrassing that it just goes so fast, but what did I do? No, that's nothing. One thing I would like to point out, yes. 50,000. 50,000. 47,000 something. What you have to see is that on every example, you just have a couple thousand non-zero coefficients. So this is why there is this trick with the scale to try to benefit from that. One thing you can see as well is that I keep tracking both the training error and the validation error or testing error. In that case, I didn't make the difference. And I use this as a hint that I'm finished. So see, it's starting to go up here, and it's time to stop, even though the training error keeps going down. So no, that's one of the good reasons why you want to measure these things all the time and track them. So the second set of results So that's for a log loss classifier. The only thing that's changed is the loss and the regularization factor. And the part that's interesting, what? Yeah. The part that's interesting here is that the log loss is continuously differentiable. So you can apply a lot of the tricks, the classical tricks of optimization that work only for very smooth functions. And this Tron algorithm, which is the previous thing that was in liblinear, now they changed to something that's more stochastic. That's truncated Newton method. It's a solid optimization method that's well known and that's certainly good. Works in about 30 seconds, which is actually faster, or 44 seconds depending on the stopping criterion you choose. But the stochastic gradient does it in 2 and something seconds. So, yes.
Do you know how much the speedup is affected by the stochastic, which is this sparse trick?
Oh, they use the sparse trick too. All this code uses the sparsity trick.
So it is that
Yeah.
sparsity trick, not
The sparsity trick is all these pieces of code use the sparsity properly. Now, the opportunity to use sparsity are a lot higher in a stochastic gradient because it's so simple. But they wouldn't even come close if they didn't. So if we look more closely at what's going on. So that's the log loss thing. On the x-axis, there is the optimization accuracy, which is the difference between training cost and optimal training cost on a log scale. And that's the training time. And if you look what the optimization algorithm does, the good one, it's clearly superlinear, meaning that it's not a line. It goes below the line, meaning it goes faster than exponentially. And it's quite impressive because in something like 1 minute, it's going to give you 10 digits of accuracy on the error. And the stochastic gradient starts extremely fast, but if you want to have an accuracy that's better than a certain thing, it's hopelessly slow. You would wait months to have something like 10 digits of accuracy. But the thing to observe is that if you look at the expected risk, which is the risk measured on the testing set, it goes into an asymptote quite early. Actually, it goes on an asymptote before SGD runs into trouble. And all the meaning of this derivation, the asymptotic things, equaling the errors and everything, is something that tells you that it's going to be always like this. You're going to asymptote with the expected risk long before SGD is in trouble compared to your standard optimization method. And this is what makes it a good learning algorithm and a very poor optimization algorithm. So I have some more experiments. There was Patrick Hafner, who has some data sets that were data sets for, well, I think the biggest one is a machine translation thing. This one with 1 billion examples and 250,000 features. And he used libSVM, I would take days. And he has this Yama SVM, which is a kind of parallelized SVM with a very sparse, which is something like, these are seconds. So that's about 10 hours to 12 hours or something like that. He has a max entropy method that's less accurate than the SVM, but for linear system, he says it's not bad. And the plain SGD is 7 seconds in this set. So that's pretty clear. Then I had complaints from Olivier Chapelle. And Olivier is this very smart guy who always finds what's wrong. And what's wrong in my test is that I said that if you want to compare, you should optimize for every algorithm, take the best number of examples, the best accuracy, the best everything. And he told me, for the batch algorithm, you didn't take the best number of examples, you took them all. Do you need all these examples to achieve this kind of accuracy? And he advocates a batch conjugate gradient method that's actually quite smart, which is designed to start up extremely quickly. So I tried with various numbers of examples, and you see the kind of curves that I've showed symbolically on the first graph. So that when the number of examples increase, you start slower, but you go lower. And what you see is that if you use 100,000 examples instead of the all 800,000, you pretty much go there in sort of 10 seconds. Now, the thing that's nice that the stochastic gradient is closer to the envelope of this thing. And there's a good question, is why? And we'll come back to that later.
So the blue line is on the full data set, and these are...
The blue line is on the full data set, but you know, it's stochastic. I already has quite a good result before even seeing the full data set.
And these are samples, any 1 million sample?
These are random samples of 10,000, 30,000, 100,000, 300,000, and everything. And you just train on a random sample with a conjugate gradient.
Are there ways where you can pick a better sample than a random sample, and then
Aha.
hypothetically, then that works?
That's a good question. I'm hoping that there is a section I haven't written in the slide that I'm planning to discuss at some point about resampling the data. Like, I can give you a very simple intuitive example. Suppose you have a data set with very few positive. You have less than 1% positive examples. Now, you need to have a loss function that's set up so that you don't, it's not better to all declare them as negative. So you need to have an asymmetric loss function. But even so, drawing examples randomly is pretty silly because you would get 99 negative for 1 positive. And that's not the right proportion because close to the decision boundary, the proportion of positive and negatives is about the same. So if you look at the distribution in something like this, it's going to be something you're going to have a mass of negative and a couple positives. The decision boundary is going to be around here. And in the vicinity of the decision boundary, the proportion of positive and negative is about the same. So, well, you can just resample. And you can use, actually, I'm changing my lecture. You can use a property that's very silly. There is a trick that's very silly. So you try to optimize something that has this form. Now, suppose you resample. You have a resampling function. So that's your new resampled stuff. Well, you do this. So it's the same function. So if you decide to show some examples more, you can simply do it, provided you reduce the loss by the same proportion. And you just optimize the same function. Now, the good question is what impact this has on the learning speed. But for this, we need to speak about learning speeds more precisely.
I also have something to talk about examples when we go
So, what can I say more about this? I'm going to come back on that one. I'm going to speak about little tricks. One of the things is choosing the Gantt schedule. So these days, I'm using things like this, like gamma 0, 1 plus gamma 0 lambda t to the minus 1. Why this? Well, first, it makes sure that when you start t equals 0, the first gain is gamma 0. So you can choose it easily. And you want to choose something not too large because you don't want to go very far away at the beginning and then crawl back your way through the... And there are little tricks, for instance, if you ensure that the norm of every pattern, x squared, is 1, you can easily see that the covariance matrix is going to have trace less than 1. So all its eigenvalues are less than 1. And so you know that if you gamma 0 is below 1, nothing really bad is going to happen. So I take 0.1 and that's it. The second thing is the gamma 0 lambda t. So There's something you're going to see in the calculation in the next hour. If we have a gain on the form eta t minus 1, that leads to a worst case speed that t to the minus mean of 1 to eta lambda mean, when lambda mean is the smallest eigenvalue of the Hessian. So if 2 eta lambda mean is too small, you can go very slow. So you want to choose eta large enough. Now, of course, when you choose eta large enough, you have to be careful because the first values of the gamma could be very large. This is why I have all the trick to make sure it starts at gamma 0. And because we have a regularized loss, we know that we have a minimum curvature that's given by the lambda parameter of the regularization. So that's a way to make sure that, because I know that lambda is greater than, no, sorry, it's the other way around. Lambda mean is greater than lambda. I can use my lambda there and make sure that the eta is greater than 1 over 2 lambda mean, and then I'm fine. There is actually another way to do these things, but I'm going to describe it later. So now I'm going to speak about conditional random fields. So they're interesting in that setup because they're linear systems. So since we're discussing gradient descent in a linear system, it's quite good. They can be very high dimensional. And typically, you have a lot more parameters than examples. Like if you take the Cone LL 2000 chunking tasks, so the task is you have a sentence, and you want to find chunks, segments in the sentence that correspond to syntactically correlated words. Like, well, the bottom segmentation in noun phrases, verb phrases, and everything, basically. You can see this as the lowest layer of a parser. And we have about 100,000 training segments in 9,000 sentences and 25,000 testing segments in 2,000 sentences. But the dimension of this, after you represent the sentence in the traditional CRF setup for this task, but the dimension is about 1.6 million parameters. And the features are basically n grams of words and parts of speech tags at various positions. So traditionally, the way people would optimize this is to use the LBFGS algorithm, which is limited storage Boyden whom? Fletcher, yeah. Boyden, Fletcher, Goldfarb, Shano, which is a sophisticated optimization algorithm that's designed to efficiently optimize continuous functions. So the loss is this CRF loss that's related to a log loss, actually. And that would take something like, well, a little bit more than 1 hour. And the SGD program, which is, well, a bit more complicated than the one you've seen because it's CRF, so it's a more complicated structure, but it's still a single file, takes about, well, 10 minutes. So there are a number of tricks. Some of them are quite amusing. Traditionally, when you do a CRF, it's connected to the hidden Markov literature. And the way you compute the updates is using the forward-backward algorithm. But if you apply the forward-backward algorithm in a relatively simple way, it turns out that you perform 3 multiply add per arc in the graph. Well, if you compute the gradients, like just a derivative and a chain rule, you just do 2. So it turns out that people notice that, and in the smart forward-backward implementation, they managed to do 2 only. But I find amusing that just doing the gradient is actually more effective at computing the gradient. Well, so I discussed that already. And in that case, I don't have the case where I know that my patterns are going to have norm 1 because they're very variable, depends on the expansions of the features that's in the CRF and everything. So I cannot use the trick of choosing gamma 0 a little bit below 1. So I'm using the secret recipe. And the secret recipe is the most trivial thing you can think of. Is that the size of the sample, the size of the training set, doesn't change the math of a stochastic gradient. The size of the training set doesn't play a role. It's the number of iterations that plays a role. So you can choose a constant gain, and you pick a random subset of your data, small but large enough to have something representative, and you try things. You try various gammas to see how it starts, and you choose one that reduces the cost nicely and robustly. And you use it for the next 100,000 iterations. And after 100,000 iterations, or 1 million iterations, I mean 1 million examples, well, you stop and you do it again. It's very silly. So in my benchmark code, I do that at the beginning, and then I have a 1 over t. That's also a good way to check the gradients. I don't know how many times I got the gradients wrong before I wrote that thing. Now, there is also something about the engineering part. So in the piece of code I've showed you, there was a trick to use sparsity. So if you have a sparse linearized VM, you basically can perform the update in 2 steps. Actually, it's 2 before 1. And the first one, because the gradient is sparse, is cheap. The second one is more costly. So you've seen an example of the solution number 1, which is to represent the vector W as the product of a scalar and a vector, and just do the thing simply. There is a solution number 2 that's connected actually to this resampling. You can consider that the part of the update that corresponds to the regularization factor is just like a special example. And you have the same number of special examples as real examples, and you just draw randomly in this modified distribution. But now, these special examples, I have a lot of them, and they're more costly to process. So I can just use the trick that's on the paper here, which is the trick of resampling. And I decide that I have a lot less of my special examples, like just 1/10 instead of half of them. And I just increase the update, or the effect of the update on of the regression update by a coefficient that corresponds to the way I downsample it. And by balancing these 2 terms, I can change the ratio between the sparse and cheap update and the costly update at will. So, and empirically, both work about the same. OK, with 10 minutes to the break. What I'm going to do, it's not next hour, we have a lunch first.
Yeah, 12 o'clock lunch break and then come back.
OK, so I go back to the thing here. OK, so that's going to be for after the lunch. Maybe I can answer questions now if you have some. If you have more questions.
So you talked about how to select the E and so on. How do you stop?
How do you stop? I use the early stopping and validation set.
So
Pretty much systematically.
So you just keep on.
I track a validation set, and I stop that way. If you continued for more, it wouldn't change that much. Just.
Is it because the heater details are so small that your updates are?
Because the what?
Is it because the eta becomes so small that your updates don't change anything?
No, they change things. It keeps moving. Like I'm going to do it for longer here, so it's loading.
Because like in your case, already in the first run through the data set, you've already achieved pretty close to the object, right?
Yes.
What 5 point? There's like some second-digit percentage varying, but nothing more.
Well, actually, I'm getting a bit better now. So if you look at the, let's see. Let's look how it is.
It's like 5.1, and after the first.
So first time I started at number 5, where the training cost was 0.12 and testing cost 0.14, but the misclassification 5.19. If I go on, well, see the misclassification starts to go, well, it go down again. That's good. So maybe I didn't stop early enough.
You're only getting like second-digit accuracy, right? Like 0.5.
Yeah, it's details at this point.
Yeah.
But
Like already in the first iteration, you're somewhere in 5, or the first or second.
Listen, you start to look at the moment where the validation error goes up, and then you do twice that.
I see.
There is plenty of room. Just it's not that I have to wait 6 hours. What you can do is save opportunistically. So whenever you get a lower validation error, you save a snapshot of your weights and you go on. And after a while, a predefined time, you're going to have the best network you can have in this time. Yes?
Like, what improve the result if you could use the same sort of criterion for example, cross-validation? Here we don't use cross-validation, right?
Here, no. I have 800,000 for training, and what I call test is validation, and it's 25,000. Different. Cross-validation is difficult to use because in cross-validation, you need to retrain. You need to retrain on the set. But if you think about it, cross-validation is interesting. The jackknife method is interesting when your set is quite small. When the set is large, this is a plain holdout set is probably better. And the reason for that is that when you measure the performance on the validation set on the same holdout set all the time, you have a much finer confidence interval. That's the first thing. The second thing is that if you're in a situation where your problem is the time, the computing time, rather than the number of examples, there is no problem having a validation set. You have virtually infinite quantities of examples. The problem is that you cannot use them all. So that also calls for a different approach to validation when you have a big problem or small problem. For a big problem, just a holdout validation set is certainly better.
Is there actually a paper you can recommend on model selection strategies?
Model selection strategies for...
What you hinted at, that for small data sets, it might be worthwhile to consider class validation, but for bigger ones.
Well, I don't want to speak about small data sets. I don't like them. No, serious. Here is why, and that's a long-standing choice that I've made. If you have a small data set, then the fair comparison is everything people did in statistics, and they did a lot of things. And in addition, because the data set is small, there is just so much you can do. And so you're not going to have fabulous gains. You're going to scratch little things. Now, if you look at the opportunities that we have by looking at large data sets, it's much bigger. When you have a large data set, there are two things you can do better. Well, you can use the fact that it's large to do things a little bit more accurately, but you can also use the fact that it's large to do more interesting things. And this is not something I've addressed at that point. So you have to do things fast so that you can use the large data set, and then you have to use the opportunities of the large data set to do something more interesting. And this is where you're going to have the big gains. You're not going to change the world by scratching a fraction of a percent on a statistical algorithm that people have known for 20 years, or 40 years, or 50 years. That's my point of view.
So in these data sets, I see that you don't have a validation set. How do you choose the validation set? And how does it affect the results if you do something from the data set?
Well, you choose randomly a validation set, no?
And that's it. So you choosing another validation set, does it affect your results, or you didn't try this?
The question is stability with respect to the validation set. Well, it depends on the size of the validation set. The validation set, until you start optimizing too hard on it, it's just like a law of large numbers. So you can have confidence intervals of what it says, of the result it says. You can have you can do paired tests to decide that the system that you have on epoch 15 is whether it's the one you have on epoch 14 is actually better than the one on epoch 15, and because they pair test on the same data, they can be quite small. So you don't really have much of a question there. But you have also to consider that there is a subtle difference. When you use a validation set, a holdout set, what you controlling is the performance of the system you produce. So here I'm able to say my system, the system I had at epoch 14, it might be better than the one I had after epoch 15, because the validation set serves as a sample of the performance. If you do something like jackknife for cross-validation, that involves the training procedure in the process. So what you control is the full process. You're saying my training technique is going to deliver results that I believe are going to have this kind of properties. There is a subtle difference that is a bit underappreciated and doesn't mean exactly the same thing. I don't know if it's clear. So when you do jackknife, because the training is part of the procedure, you validate the complete system. You validate the estimator, the training algorithm itself. When you do something like this, just a holdout set, you can get very easy confidence interval, but you validate the product of the algorithm. So if you have an actual problem to solve, this is the product of the algorithm you want to have. If you have to write a paper, you want to prove that your algorithm is good, that's another story. Yes?
Categorize the algorithm SGD in a highly imbalanced data set.
If you have a highly unbalanced data set, there are two things you need to do. The first one is to have a loss function that's asymmetrical, to clearly represent that you give different price to errors of type 1 and errors of type 2. That's standard. The second one is that it's certainly a good idea to equalize in the sampling the number of positive and negatives and compensate by adjusting the loss function. So if you decide to oversample the positive because they're very rare, you want to reduce the loss function by an equal coefficient, means reduce the gradients by an equal coefficient. Yes?
So with graphical models more generally, I think this is not my issue. I have a naive question potentially. When one listens to progress in supervised learning, one sees lots of rich structures, hierarchical structures, and also one sees pretty sophisticated algorithms. Listening to you, is there hope that we can build rich structures but have a very simple learning algorithm that works?
We've done that quite a lot. We have a number of results, like the Czech readers of the 90s was a complex structure with a simple stochastic gradient. The natural language processing task of Colobers are very complex structures with a simple algorithm. And the reason we use the simple algorithm is because it gave us more bang for the buck. When you optimize, like for instance, like the Colober natural language system, an unsupervised loss was semi-supervised with 1 billion unlabeled samples and 1 million labeled samples. If you use a sophisticated algorithm, just the time to go over the 1 billion examples and you're already out of the competition.
So the implicit claim is that it's the structure that's the advantage, not those sophisticated algorithms.
Probably, yeah. On the contrary, in many cases, my opinion is that there was a regression in performance from using more principled optimization algorithm. That this kind of things, linear with stochastic gradients, were things we did 15 years ago, or 20 years ago, or 25 years ago.
How do the proponents of those sophisticated algorithms respond to this?
They've lost. They provably lost, that's my point. And if you look at what's happening now, like you have a lot of efforts in doing sophisticated stochastic algorithms. But there are some things that are, the level of sophistication is not much. It's some smart averaging methods, or averaging the gradients, or averaging the results. And there is a lot of work by, there is the line of work by Nemirovsky, Shapiro in their Siam paper from, I don't know, was it 98? So about the same as mine here. And there was There is a line of work for sparse system by Ling Qiao, and that's still inspired by these dual methods. But there's still algorithms that fit in one page. Huh? They're very simple. Well, it's lunchtime.